We present SynopFrame, a multi-scale time-dependent visual abstraction framework for analyzing DNA nanotechnology simulations. It consists of 7 linked viewports and a controller panel. To develop SynopFrame, we first collaborated with a domain expert to analyze the tasks and challenges associated with analyzing oxDNA's trajectory, one of the DNA nanotechnology simulators. Here, we show the design of a cube structure in the widely used design tool, CAD-Nano. After converting it into the oxDNA format, this is how it is visualized in OxView, a widely used viewer in the domain. We can see a lot of clutter and occlusion in the current visualization. There is also a discrepancy between CAD-Nano's design view and OxView's. These issues worsen when it comes to the dynamics. The overall task of our study is to develop a way to enable analysts to easily perceive and understand what has happened during the simulation and gain actionable insights. We refer the audience to section 4 of our paper for more details on task and challenge analysis. We then reason from the established representations to build a visualization abstraction space. We have ONT representation from OxView, schematic 2D from CAD-Nano, snake from Adenita, and hit bar from Adenita. These representations can be thought of in terms of 3 orthogonal aspects, or axes. The first axis is granularity. In ONT view, each individual element is a nucleotide. In schematic 2D view, each of the 2 parallel straight lines represents one continuous double helix. In snake view, each snake represents one strand. Coarser than a strand, we can also have one level to represent the whole design, which we call assembly. The second axis is the visual idiom. In schematic 2D view, straight bars are used. In snake, curved snakes are used. In ONT, geons, which include spheres, cylinders, and cones, are used. The third axis is layout. In ONT view, each nucleotide is at its actual precise position. In schematic 2D view, each nucleotide, or rather, each helix is at a schematic position that helps better understand the relations between itself and other helices. In hit bar view, each nucleotide is positioned sequentially according to its index. We refer the audience to section 5.1 of our paper for more details about the levels on each axis. We then use these 3 independent axes to form an abstraction space, SynopSpace. We move the labels around to avoid clutter and occlusion. We then adapt existing representations and design new ones from the space to fulfill the tasks and tackle the challenges. The representations we have developed are ONT, which resides at Synop point 1 in SynopSpace, snake at Synop point 2, schematic 3D at Synop point 3, schematic 2D at Synop point 4, hit bar at Synop point 5, and progress bar at Synop point 6. For schematic 3D, we perform a series of transformations from the input center of mass data to build the final geometry. We refer the audience to section 5.2 of our paper for more details. We then link all the representations, as well as the conventionally used principal component analysis plot via the time axis to form our approach, SynopFrame. We categorize the hydrogen bond status, which is a property that can be calculated from the trajectory, into 5 categories and apply a different color to each category. We provide details in section 5.3 and appendix F of our paper. The controller panel can be used to control these colors and a handful of other handy parameters. With SynopFrame, for a cube design with 16,122 nucleotides, after playing or fast-forwarding through the simulation, we can immediately observe a knife-cutting pattern in the middle of the cube, which partially explains why the domain experts have difficulties assembling it in the lab. For an RNA tile design of 132 nucleotides with 2 conformations, after playing or fast-forwarding through the simulation, we can observe the 2 populations very well in SynopFrame and gain actionable insights. Finally, we sent a case study video to domain experts and collected their feedback on our approach. For more details about both case studies and feedback, please refer to Section 6 and 7 and Appendix G and J of our paper, as well as the other supplementary video. We uploaded all the mentioned materials to OSF and open-sourced our approach on GitHub. Thank you.